Hello and welcome everyone. Thank you for joining us for our expert sessions. These short webinars take place every week and last no more than 30 minutes, bringing you valuable insights from industry experts. Today's session will be presented by Sunny Solanki. He's a senior technical manager at I-Gard. Sunny is an electrical engineer from McMaster University with 8 years of experience in protection systems and relays. Throughout his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their designs to enhance personal and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high resistance grounded system, low resistance grounded system, hybrid HRG system, ground fault and arc flash relay protection system, resistor based solution, and personal protective products. We are excited to have him here today, and we appreciate your participation. Without further delay, I would now request Sunny to take over from here.
Thanks, Devansh, and hope everyone had a nice Thanksgiving weekend for those in Canada. My name is Sunny. I'm the Senior Technical Manager for I-Gard, and today we're going to be talking about arc flash risk and magnitude reduction with high resistance grounding and our optional arc flash detection module. So to start off, the National Fire Protection Association defines arc flash hazard as a dangerous condition associated with the release of energy caused by an electric arc. Arc flash occurs when there's a breakdown in the insulation between two conductive objects. This breakdown can be caused by a number of factors, including human error, equipment failure, or environmental factors such as moisture or dust that result in phase-to-ground and/or phase-to-phase electrical faults. So the questions that come to mind is, what is the probability of an arc flash occurrence? And if it does occur, what would be the magnitude of its severity? In NFPA 70E, in Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and enabling achievement of an electrically safe work condition. NFPA 70E also has a mirroring standard in Canada, which is CSA Z462. This is a standard for electrical safety in the workplace. So basically, they're giving ideas to consultants on how they should reduce the likelihood and magnitude in Annex O.2.3, which list out 9 different incident energy reduction methods. Of the 9 listed, we're going to be focusing on reducing the likelihood of exposure and reducing the magnitude or severity of exposure. Now, when it comes to reducing the likelihood of exposure or reducing the probability of an arc flash occurrence, we can look at high resistance grounding, which is one of the only incident energy reduction methods of the 9 listed that is reducing the likelihood of exposure. All the other incident energy reduction methods listed are acting after the fact that the arc is already in the system, and it's looking to reduce the magnitude. So when we place that impedance in the ground return path and limit fault current to 10 amps or less on a system that's 5 kV or less, we leave insufficient fault energy and thereby help reduce arc flash hazard levels. The only blind spot for high resistance grounding is that in the case of a line-to-line or a line-to-line-to-line failure, the resistor at the source that's connected between neutral and ground is no longer in the path of the ground fault. So if I have 2 feeders, for example, feeder 1 phase A faulted and feeder 2 phase B faulted, the 2 faults will circulate to ground and circulate between each other and grow to thousands of amps. The NGR will not see any of that current, and that's why phase-to-phase and 3-phase failures are not seen by an HRG system or be impacted by it. So although HRG can reduce the likelihood of exposure for 95% of the cases being phase to ground faults, it's not able to do the remaining 5% when it comes to phase or three-phase failures. So we need another incident energy reduction method to go alongside the good task that high resistance grounding is doing to cover the remaining 5%, where 95% is being covered by HRG and the remaining 5% can be covered by an arc flash sensor. So far, we know that the standard high resistance grounding unit is able to reduce the likelihood of arc flash, but by itself, it can't reduce the magnitude of an arc flash. So let's take a look at how we can reduce the magnitude of exposure. Of the 9 incident energy reductions listed, we chose the arc flash relay. Arc flash relay typically uses light sensors to detect the light produced by an arc flash event. Once a certain level of light is detected, the relay will issue a trip signal to an upstream overcurrent device. So what we're trying to do here is we're trying to reduce the exponential upward movement of the power or energy associated with an arc flash incident by cutting off the power upstream such that the arc doesn't build up as fast. So this is where our arc flash relay comes in. As you know, the arc flash impact, the power of an electric arc, which shows how much damage it can do, depends mainly on 2 things: how long the arc lasts for, and how strong the current is. So the longer the arc and the stronger the current, the more destructive the arc can be. So you can see that even 0.1 seconds or 0.15 seconds can be problematic. 0.2 seconds, you can have steel fire. In IEEE 1584, they have intermediate incident energy calculations for different voltages. You can use these to determine how much incident energy there could be in your system. The key thing is that we want to reduce the damage effect. So if we reduce the arc's buildup using arc flash relays, we can reduce the time that the arc is in the system and then try and reduce the energy effectively. So if we reduce the time to 35 milliseconds, for example, there's no significant damage to person or switchgear, which can often be returned to use after checking the insulation resistances via measuring. So we reduce the incident energy to 2.9 cals per centimeter squared. For 100 milliseconds, there's small damage, requires cleaning and possibly some minor repair, and we're reducing the incident energy by 8.31 cals per centimeter squared. And if we are reducing to 500 milliseconds, there's large damage both for person and the switchgear, which must be partly replaced, which is at 41.58 cal per centimeter squared. So this is based on a 50 kA maximum voltage fault current on a 480 volt solidly grounded system at 18 inches of working distance. And the arc burning time is the sum of the time to detect the arc and the time to open the correct breaker. An arc is accompanied by radiation in the form of light, sound, and heat. Detecting these can help identify the presence of an arc. Analyzing visible light, sound waves, and temperature changes can reveal if there's an arc. So even pressure sensors are also viable in this situation to determine if there's an arc in the system. However, the pressure sensors are not as fast as the light sensors. The light sensors are pretty fast, between 1 to 10 milliseconds, depending on how fast your switching scheme is at your breaker. Usually there's 5 cycles, but I've seen that there's some 3-cycle breakers as well. And the energy developed by the internal arc generates heat and pressure based on the curves here. So we have short circuit current denoted as A, the arc voltage, which is going to be B, and then internal pressure, which has an impact directly off the bat and within the first cycle of this wave. So our DSP system is a very unique solution involving advanced high resistance grounding. So this is not your standard high resistance grounding relay. It has various capabilities in monitoring the resistor, monitoring voltage between phase to ground. It also monitors individual feeders for ground fault pickup. It has second ground fault protection. And we've also included an arc flash module which can connect to up to 21 sensors across 7 channels, three sensors per channel. We can use fiber optic sensors or pressure sensors to connect to this relay module, and this would be useful within the switchgear that the CTs and the feeder connections are connected to. In this case, with high resistance grounding and the combination of the arc flash relay, we can mitigate 95 to 98% of arc flash incidences by picking up on phase to ground faults through our HRG system, which will limit fault current to 5 amps. And phase to phase and 3-phase failures can be picked up by the arc flash sensors. So the arc detection module, the aim is to diminish the incident energy, thereby reducing the magnitude of the arc flash by tripping the upstream breaker. Arc detection module proactively identifies and notifies of electrical arcs in the system by monitoring light and/or air pressure, providing an added layer of security for your operations. So our module is called the DSP ADM, and it can use point light sensors, modified point sensors with fiber optic tails, and IPS2 or IPS4 pressure arc sensors. The theory behind it is quite simple. The ADM detects the light or the pressure from an arc flash. The system determines the intensity of the light, and the system sends signal to trip the breaker if a certain threshold is exceeded. So with the advanced high resistance grounding offering, we can also provide reduction in the magnitude of an arc flash with the utilization of an arc flash sensor. And this will provide a more secure system than just the standard high resistance grounding offering. Now, here's the case study for advanced high resistance grounding. So traditional grounding systems in industrial setups pose high arc flash risk due to uncontrolled fault currents, particularly for solidly grounded systems. And for ungrounded systems, it's possible that there could be 2 faults in the system at the same time, since it's very difficult to locate faults in an ungrounded system. So with advanced HRG systems, they offer a safer alternative by limiting fault current, reducing arc flash hazards, and improving fault management. So our purpose of this case study is to highlight how advanced high resistance grounding systems significantly reduce arc flash hazards in industrial electrical systems, while also enhancing safety, reliability, and fault management compared to traditional grounding methods. So this article uses IEEE standards and real-world comparisons to demonstrate how advanced HRG minimizes arc flash risk by limiting fault current, enabling safer fault detection and preventing system-wide shutdowns during fault condition. So we're using our arc flash relay as well to pick up on arc flash via fiber optic cables and pressure. The high resistance grounding system is employed at the source between neutral and ground to lower fault current levels and prevent arc restrike. As you know, solidly grounded systems pose the highest arc flash hazard, especially in 488 volt and 600 volt systems. Neutral path monitoring ensures that the resistor is there to do its job when a phase to ground fault occurs. So we're monitoring for both open circuit and short circuit conditions. In the case of an open circuit resistor, your system becomes ungrounded, and that's not a very good thing to happen because your protection schemes downstream may be unable to operate in an ungrounded system. In contrast, if we have a short circuit condition, our system becomes solidly grounded and we're no longer limiting phase to ground faults to a particular value. There's also feeder level fault isolation and time delay trip settings with respect to second ground fault protection. If we see that there's two feeders experiencing faults on different phases, we can selectively trip the lower priority of the two feeders to make sure that we still have some continuity on one out of the two feeders, the one that is most important. And the way that we do this is our feeder modules have a 100 amp pickup, such that when that 100 amp threshold is passed, then we automatically send a trip command to the lowest priority of the two seeing that 100 amps. Now, if you didn't have the DSP system in place, your LSI breaker will pick up through the instantaneous function and trip at 6 to 8 times its current level. But it still takes time to get to that 6 to 8 time current level, so our selective tripping method is slightly faster than that instantaneous function. The conclusion is that advanced HRG systems are the most effective solution for reducing arc flash hazards in industrial environments. And by combining fault current limitation, intelligent fault isolation, and proactive monitoring, especially with arc flash sensors, they offer unmatched safety and operational continuity, making them a superior choice over traditional grounding methods. Now let's go into our questions. What is the sensitivity of these light sensors? Will there be false tripping? The sensors are capturing the particular spectrum of light emitted by an arc flash, so it's not susceptible to camera flashes falsely tripping it. So I'm not sure what the exact pickup value for the measurement for how many lumens it takes to activate this arc sensor, but I can get that to you if you provide me an email. Now, if we have switchgear lineup, let's say with 16 breakers, do we need to install sensors in all 16 cubicles and just one module? I would say that you should max out on the number of sensors based on hopefully having, you know, 2 sensors per cell that has, like, let's say 3 breakers. If a cell just has 1 or 2 breakers, maybe it can get away with 1. But the more sensors that you have, the better protection and area you can cover. In some cases, some barriers within the switchgear cell may, let's say, block the light from getting to our sensors. So positioning is obviously going to be very important. And that's how I would suggest you to go about it. Some people also use a combination of light and pressure sensors because if they feel like the barriers may be blocking the light, then at the very least the pressure can be picked up. How does the unit communicate back to the breaker? Is it a hardwired connection? So we use dry contacts that are wet with voltage, and then we apply a signal to the shunt trip coil to pull in, basically. So in this case, we're kind of dependent not only on our detection time, but also on the overcurrent device's trip time as well, whether that's 5 cycles or 3 cycles. Are there any other questions? All right, thank you for joining us today, and we will be the presentation is available, I believe, as part of the handouts, if I'm not mistaken. Devansh, do you know?
Yes, I have shared in here.
Yeah, so try and look in the handout section so you can pull those up, and then I think we're going to be sending an email as well, if I'm not mistaken, right, Devansh?
Yes, we will be sharing the recorded session and along with the documents.
Okay. Thank you guys. This will be repeated again at 1 p.m. and also stay tuned for next week's presentation. I appreciate it. Take care.
Thank you, everyone.